I can tell you that almost within a decade, there will be a claim that we have detected life. I think we will have the data to do that.
You're listening to The Cosmic Cast. Hello and welcome back to The Cosmic Cast. I'm John Panay-Fisher and I'm joined as per usual with the lovely Marissa Lowe.
Hello.
And the fantastic Tom Harvey.
How you doing?
And all the way from Birmingham this week, we have a fantastic guest for you all, Dr. Amaury Triaud. How's it going?
Hello, very well.
So you came up from Birmingham this morning.
Yes, easy.
Excellent. And you study exoplanets, which is an absolutely fascinating topic.
I agree. I think in 25 years, even this year, we received as a field the Nobel Prize for Physics, recognizing, I think, all the advancement that happened.
Yeah. So I guess are you in the Department of Astronomy then?
That's correct, Physics and Astronomy.
Yeah. So how did you get involved with exoplanets in the first place?
Well, I remember not the first discovery, but I remember the second one as a child.
Mm-hmm.
And I remember really calculating in kilometers where it was. And I was sort of fascinated by that already then. And I knew I wanted to be an astronomer. I moved to the UK because you could do astronomy in undergraduate level sooner than in France. And while I was doing my studies, St. Andrews got involved into a search for exoplanet called WASP, the Wide-Angle Search for Planets. And they needed collaborators, notably in Geneva, and I proposed to go there to initiate the collaboration, and that's basically how it started.
That's amazing. So I guess just for some of our audience that may not be too aware of how exoplanets are detected, how are you able to see such a small object that's so far away in the sky?
Yeah, so the main method nowadays is looking at the shadow that the planet casts, and the planet will pass in front of the star, and as it does so, it casts a shadow. The bigger the planet, the bigger the shadow, the deeper the shadow, and so you can measure the size. If the shadow repeats, then you measure the orbital period. If you measure two sets of repeating shadows, then you have two planets. And then if you measure a slightly different size, apparent size of your planet with wavelengths, with different filters of color, then you get to know whether the planet has an atmosphere, etc. There are other methods, but that one is by far the most used. It has led to the most detection, and it's leading to the most outcome as well, because it doesn't just give you a chance to detect the planet, it also gives you a chance to probe the atmosphere of the planet from Earth without ever having to go there, which is
it's
rather
just incredible. Yeah, absolutely amazing.
So just for some other context, how many exoplanets have been detected then?
We know, I think, of confirmed bodies between 3,000 and 4,000. I'm not too sure on the exact numbers. Also, the confirmation methods differ from institute to institute. But yeah, we know many.
Yeah, wow, okay.
Yeah, that's
incredible.
And
what sort of sizes do they range from? How small a planet can we detect?
So the biggest we have for the top range, that's the easiest to identify, is about twice the radius of Jupiter.
Wow, okay.
So that's about 20 times that of the Earth, roughly. And that planet is called WASP-17. It's a gas giant very close to its star. It's been irradiated so much that the atmosphere has expanded, essentially. And we don't find any more planets bigger than that. In terms of smaller size, then some of the smallest have the size of the Earth. Mm-hmm. But I think the actual smallest is probably about the size of Pluto or something of that kind, something in between, a dwarf planet, an asteroid, something like this. And it's because it was found transiting a small star called a white dwarf. Mm-hmm. A white dwarf is what we call a stellar remnant. It's the former core of a star like the Sun. And the white dwarf has about the size of the Earth and the mass of half of the Sun, so a very dense object. And the advantage of a small object, a small source of light, is that you can find something, a smaller shadow, essentially, passing in front of it. So you can get very, very small, in fact. There's another object that we suspect is smaller than Mercury as well, that has been detected. And the reason we don't actually detect the object itself, what we detect is material evaporating from the surface. So it's so close to its star that silicates themselves become gaseous, they sublimate. Mm-hmm. And so we see a tail, essentially a rocky comet of some sort. And we see the tail passing in front of the star, and you will know well that a small object, although they're very small, if they're very numerous, will cast a very big shadow, like comets. We see them very well.
Yeah, wow.
Although the dust that forms the tail is only a few micrometers, probably.
Yeah, it's amazing, really. So, I mean, I guess something that I've read about, I don't know how true this is, but I've read that this solar system isn't necessarily that representative of some of the solar system compositions we've seen in around other stars.
Well, it's certain that the solar system doesn't look like the majority of exoplanetary systems. So if you look at just sun-like stars, we already have surveyed about, we know that 2/3 of sun-like stars have something that qualitatively looks different from the solar system. They usually have something more massive than the Earth within the orbits of Mercury. And that's really surprising. But on top of that, we know that half of the sun-like stars have another stellar companion, so they're binary stars, and we don't really know planet formation in this setting. And we know that stars that are very small, like less than a quarter the mass of the sun, are the most numerous stars out there, and they have planetary systems that look different from our own. And the one we talked about earlier, called TRAPPIST-1, has 7 planets the size of the Earth, which is crazy when you think of it. Right? Imagine the solar system with 5 more versions of Venus and Earth, right? Wouldn't that? It makes space opera real in a way.
Yeah, I mean, I'd love to see some of the planetary views in the night sky of some of these big bodies up ahead, and so it must be phenomenal to see.
Yes, yeah. In TRAPPIST-1, the planet E and F, so the somewhat outer of the system, are so close that they're only at conjunction when they come at closest, only 3 times the Earth-Moon distance from one another. It means that if you were to sit on that TRAPPIST-1e and look up at the F planet pass in the sky, you would have twice the area of the moon.
Yeah.
And with a small telescope, like 30-centimeter telescope, almost as wide as your hand can stretch, you'd be able to discern metropolitan areas.
Wow.
And this is just mad, right?
Yeah, I mean, it's real sci-fi stuff, but so cool. So you're involved. How long have you been involved with the TRAPPIST-1 project, mapping this system?
The TRAPPIST as a project was a pilot to something more ambitious that started in January, called Speculos. With TRAPPIST, so TRAPPIST was involved actually in the original project that I was involved with, called WASP. So the TRAPPIST telescope, to summarize, is a 60-centimeter telescope. It's located in the south part of the Atacama Desert in Chile.
And that's where a lot of the large radio telescopes and all the other sort of astronomical...
Yeah, many telescopes. Chile is the best sky in the world. It's absolutely stunning to go there.
Yes, I'll bet, yeah.
Is that because it's very flat?
No, so
very
it has
clear
mountains.
skies?
So we have high mountains, 2,500 meters. We can be above most of the weather. And we're by an ocean. So that means a more laminar atmospheric flow, which doesn't disturb observations. And very importantly, we are in a dry area, so a desert, and close to a cold ocean. A cold ocean current will also tend to stabilize the atmosphere. And if you think of a mountain range next to a cold ocean, there are not that many on Earth. And so Chile has the advantage of having something which is 2,000 kilometers long, with many mountain tops that we can use. Going there is stunning. You can see after 20 minutes your shadow on the ground lit by the galactic center, so you can see your shadow cast by 200 billion stars.
That's incredible.
If you stay even a bit longer when Venus is in the sky, you can see your shadow cast by Venus. And the old observers, the ones who stayed in the domes for several hours on end, observing optically, like with their eye behind the telescope, they say after 4 or 5 hours you can actually read by starlight. It's totally different from our location, right?
Yeah, that must be so special. Is it so when you're up high in these sort of telescopes? Is it quite difficult to correct away the Earth's atmosphere, or do we know the atmosphere so precisely that it's easy to remove from such these small measurements that you're making?
So it varies from the type of measurements you do, but the atmosphere is a big issue. The advantage that we have is that we don't resolve the object. What the atmosphere will do is blur the image. So it will basically prevent you to resolve 2 objects that are close to one another. They'll appear as one, essentially. For us, we never actually see the planet. We always see an indirect measurement. We see the effect it has on the brightness of the star. So long as we can see the star, it's all right. The thing that prevents us or annoys us the most is the column of humidity above us, because then that will change in in a color effect. It will change, affect a star that is redder, colder, typically more than a star that is bluer. And we measure and detect the planet from comparing how bright a star is to all the other stars that we see. So long as everything moves the same way, that star A and our target move and change in brightness at the same amount, then we do a relative measurement, and then we find that on the target something happened. But if it doesn't happen that way, if the sky is more patchy, or if water, for instance, will affect more certain stars than others, or at least the brightness that we see, then you can mimic actually planetary transits. And so we're very careful with that.
So this is probably quite a basic question. How do you know where to point your telescope in the night sky?
It's not basic. It takes a long time to know. It's actually, like we were just saying before, we have 200 billion stars in our galaxy. So where do you start?
Yeah, exactly.
People started with sun-like stars to begin with, then realized that many of them were binary stars. So they decided, let's just do stars exactly like the sun. Now we're trying to select others. So for the TRAPPIST and Speculoos project, we select stars that are only between 8 and 15% of the sun's mass. So very small ones. And so for that, we have to do a census. We have to know where they are. And for us, they're not that many. These stars are very faint. In fact, the closest star to the solar system is called Proxima Centauri. And it's invisible to the naked eye. You need a telescope to see it, and that's kind of crazy, right? And these small stars, they're about half of the stellar content of our galaxy, and we have never seen one with the naked eye, which is also weird, right, to think about. And so they're hard. The census is good, but not complete. And so within a certain volume, within a certain brightness for which we know we could detect a planet around them, there were not that many of them, and we've identified only 1,300. So that's our sample.
Right, okay.
So is there a particular star or star system that you would really love to try and investigate in more detail? Is there like an ideal solar system you'd want to find?
Well, as we mentioned, TRAPPIST-1 is as close to the ideal solar system that you can find. It has its own issues, but the advantage is a small star allows you to find small planets. So we found 7 small planets around it. It also makes it's easier to detect the atmospheric content of the atmospheres of the planet as well. So that's quite optimal as well. And it's among the brightest that we have of that type. And so I think just my guesstimates, there's only a 30% chance there's a better system out there. The advantage also of TRAPPIST-1 is that, so for every planet that passes in transit, so passes in front of the star, there are many systems that do not, that are face-on, essentially, like the orbit in a way that the orbit will never pass between us and the star. The chance we have with TRAPPIST-1 is that all 7 planet transits. The closer to the star, the easier it is to transit. And so we have a chance of a system that has 7 planets. It's unclear how many have that many. Very close in as well, very close to the star. The whole system is packed within 6% of the distance between the Earth and the Sun. And all 7 transits. And as a sort of, direction towards my colleagues who are theorists, if they were to do the optimal planetary system in order to check what's the influence of the flux from the star, the energy they receive, the planets receive from a star, you would scale your planet uniformly in log space. And in TRAPPIST-1, they are. And that's crazy. It really looks like a theorist's dream. And so that's probably as best as we can get.
Yeah.
That's great. So what's the main aim of studying exoplanets then?
The field is driven by the search for life elsewhere. We want to find out if there is life. Which actually, I will reframe the question in a more interesting term, because often people ask, is there life, which is a yes-no answer. I think it's a little simple and reductive. I think a far more interesting question is how frequently there is life. Is it 1 planet in 10? Is it 1 planet in 100? 1 in a million? That's interesting for 2 reasons. One, it allows you to study systems that are not sun-like, essentially. So and the study typically of TRAPPIST-1 and others, it also means that if you don't find life somewhere, you still learn something, right? So, for instance, we know that stars like TRAPPIST-1 are 3 times more numerous than Sun-like stars, and they appear to host something like 3 to 5 times more rocky planets than Sun-like stars. So we can expect that there are 10 times more rocky worlds around this strange, very exotic star for us than there are around Sun-like stars. So the most common planet is very exotic, but for someone that would be born there, we would be the exotic planet, right? A sort of rare example. Now, if somehow, stars like TRAPPIST-1 have an issue. They emit a lot of UV, a lot of X-rays, and these will impact the atmosphere, the development of life, presumably on the planet. And if it turns out that all of those planets are barren, then we know that at most it's 1 planet in 10, one rocky planet in 10 that has life. Yeah. And that's the first order of magnitude. Yeah. It's already a knowledge starting to be acquired. So I prefer that question: how frequently there is life in the universe? And then the second question we try to tackle is how planets form, because by and large exoplanets have shown an immense diversity, way more than people anticipated, and it's throwing away a lot, or making us reconsider many of the processes that we think led to the solar system. All the planets that we found are basically where people expected none to be found so far. And every time a theorist came with a new way of forming planet and trying to predict the population, they predicted, I remember when a group in Bern notably tried to do the first big model, exactly where we found the most planet, they predicted none at all. And that keeps puzzling us. And so we're challenged by nature, and we want to understand that. I think it's going to tell us, give us an indication of how common Earth is among the many outcomes of nature, essentially.
Yeah. I guess another important factor too, I suppose, is do we have a sense through some of these models of how old TRAPPIST-1 is? Is it quite young relative to the solar system, or much older? And I guess that probably has a bearing on whether we expect to see life or not as well, I guess.
So the system, measuring an age for such a star is difficult, but the best estimate that we have at the moment is about 7 billion years, so it's slightly older than the solar system. Yeah. I'll put some dampening here that the uncertainty is about 2 billion years.
Right.
So,
but still, it's not a super young system.
It's not super young, no.
Yeah, that's interesting.
When you say that we're looking for evidence of life, what sort of biosignatures are you looking for in these planetary atmospheres?
The main one that people look at is a chemical imbalance, chemical disequilibrium in the atmosphere, something that should not exist, essentially. If you take the Earth and you look at our 21% oxygen content, if you remove photosynthetic organism on Earth, it would take, in my recollection, about 10,000 years to react and oxidize the surface. 10,000 years is very short on astronomical timescales. And so we're looking for imbalances of that kind. Of course, this can be caused also by transient events and geology or the hydrolysis of water by the stellar flux. So we're looking at all sorts of them. An atmosphere that would be half CO2, half CH4, so half carbon dioxide, half methane, would be half oxidized and half reduced. And that can't happen. There would necessarily be a reaction. And so if that reaction does not take place, it's telling you that something is keeping the balance out of whack. And there is nothing better on Earth than biology to do that for you. One way that we can confirm this is by verifying at several species. There will never be one chemical species telling you, oh, there's life. We can have other traces as well. So TRAPPIST-1 is convenient because you can compare the planets from one another. So if you find that only one of the 7 planets has a large amount of oxygen, and it turns out it's more or less where we expect liquid water to remain for billions of years in that state, then we're going to be extremely interested by that. Similarly, if we find a CO2, CH4 in balance, we will be looking at it. So you will proceed, I think. Well, I don't know if we'll proceed with caution. I can tell you that almost within a decade, there will be a claim that we have detected life. I think we will have the data to do that. But what I can predict you as well is that as soon as someone will tell you, another 10 people will tell you that we haven't. And then there'll be a good debate for a few decades before we settle on yes or no. And then we'll proceed from there.
Keep going.
Yeah, I guess I guess it can be quite difficult to try and verify independently whether indeed some of these signatures are biologically driven or not.
Yes.
But yeah,
There are other a bit wacky ideas out there too. Like we can detect from a reflection of the Earth's day side on the dark side of the moon, so from what we call the Earth shine. We detect what we call the reflectance spectra of the Earth, and in that spectrum we can see the effect of vegetation. So vegetation has what we call a red edge. It means that plants basically reflect infrared, and they do that to cool down, notably. And so we can see that. So that's something that we might be able to also notice on another world. There's several things that we can. Some people are even looking at bioluminescence as well, because Earth has some emission lines that correspond to plankton activity. So there are other things that we can look at. Things that are weird, essentially. And I think the easiest. So for a long time, people were always thinking of the problem of a planet in isolation. Say, I have a habitable zone planet. How do I know there is life? But what's stunning, I think, for the Earth is you know there is something special on Earth because you can compare it to Venus and Mars and you find that it's different. And I think a comparison between planets is probably the way forward.
Would perhaps an easier way to detect life would be by hoping there's some other civilization out there that's also heavily polluting their planet relative to trying to pick up bits of vegetation.
So people have been thinking about this. Yes, it's I don't know. Like while I'm quite optimistic, like many of my colleagues, about the ubiquity of biological processes, I'm far more pessimistic about the emergence of intelligence, and certainly of a detectable intelligence.
Sure. But what's really amazing is, we were talking about this earlier, to what extent the resolution of understanding of some of these planets are. So we were talking earlier about being able to identify specific isotopic compositions and be able to even map some very crude geographical features. I mean, that's just absolutely amazing, and it's got to help constrain whether we think these planets are good candidates or not.
I would hope so. I mean, I'm very excited by how many things we can do, but I'm also very aware of some of our limitations, and I don't want to dampen any enthusiasm either. But we will have indication. We will be able to make crude maps, have some abundance or composition measurements of the atmospheres. There will always be an uncertainty because we can't see the planet. We can't. Contrarian to a biologist or a geologist, you can't make an experiment. You have to rely basically on instruments that very carefully manipulate the light of a star which has been affected by a passing planet in front of it. And so there will always be a shadow of doubt, I think.
So what would be the ideal telescope set if money was no object? Would you like to see something on the far side of the moon, for instance, or?
That's an interesting prospect. The far side of the moon would not be so useful. I think I would prefer a freestanding structure in space, because then you can observe in an uninterrupted way your planet. What you would need, I guess, if money is not a limit, as large a mirror as possible. For two things, because the larger the area of mirror, the more light you receive. And essentially all your information comes from light. So you need that. But then if you can start to have a telescope that is wide enough, then you can start resolving your planet from the star. So the moment we do that, but only for planets that are really far away from the star, young planets still hot from their birth, we can detect at a distance of 50 astronomical units from their star, roughly. But if you imagine a telescope that would be much bigger, you would be able to resolve planets within their habitable zones and even maybe features. But then those are behemoths, things that would be, I don't know, a kilometer in diameter in space. I don't think we quite have that. For me, in a practical level now, I'd rather have something of about 10 to 15 meter on the ground to limit cost. With a very high resolution spectrograph, then you'd be able to carry out all that isotope work, composition work. You'd be able to observe the planet as the starlight goes through the atmosphere, but also as it's reflected or emitted by the planet,
Mhm.
which will each give you different pieces of information and give you already a vast amount of knowledge for a cost that would be far more limited.
Yeah, that's really cool. So what kind of isotopic species can we identify? Is it mostly lighter isotopes, I guess?
So at the moment we're not doing this. We just know that we will
In
be able
theory.
with, say, the European Extremely Large Telescope, which is under construction in
Right,
Chile.
okay.
It'll be a 39-meter diameter telescope. But we hope to detect something like C12O, C13O, typically, some oxygen isotopes as well.
Yeah.
Exactly what that will tell us, I don't know exactly yet. We will be able to compare certainly to the solar system.
That's still amazing, though.
But
I
it's
mean,
amazing,
Yeah.
and compare from planet to planet. Again, life has an effect on isotopic ratios,
yeah.
and so that can become a new biomarker eventually,
Mhm.
one that is
Absolutely.
maybe more indicative than a simple abundance or chemical disequilibrium.
Yeah.
So yeah, something that we ask all of our guests is if you could be doing something other than exoplanets and astronomy, inside academia or outside of it, what would you want to be doing?
I think I love urbanism, so I think I'd be somebody involved in that.
Okay, so studying towns and cities.
Yes, exactly. How to
Mhm.
organize civic life, essentially, by
Yeah.
constructing a city.
And,
How to make sewer systems that work,
Mm.
transport systems that work, things like this.
That is a fascinating topic, actually. Yeah.
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 yeah, and to be honest, that's one of those where, as you're wandering around in everyday life, you go, "Who's responsible for thinking of these things, and
It may
how do
be
we
born
improve
out
it?"
of frustration for this kind of things.
That makes so much sense. Yeah.
Yeah.
Awesome. Well, that's excellent. That was a fascinating conversation. Thank you so much once again
Yeah,
for
thank
coming
you.
to join us.
Well, thanks for inviting me.
Well, we'll give you a round of applause and we'll see you all next week.